Video 9 will be mainly on section 2.7 in your text. I'm combining them a little bit from 2.6, but 2.7 is the section that you should read if you're reading to go along with the video. In fact, at the end of 2.7, if you're reading online and you did get into Wiley Plus, there is something called Developing Ideas, and students can go to study objective exercises and you can practice some of these things. Most of the topics we're going to cover are ones that you've seen actually more in elementary, middle school than you did in high school, but we need to bring back these ideas of numbers. We're going to be looking at the real numbers. The real numbers is the set of numbers, the largest set of numbers that most of you have considered. It's all decimal numbers. Some are rational and some are irrational, and we want to go through those definitions in this section. Well, I see that the line I had drawn on the slide is not showing, so my lines will be a bit crooked. I have to do them by hand. The real numbers are all decimal numbers, and they correspond to points of a line. Every point corresponds to a real number, and every decimal number corresponds to a point. Now, just to review, a point and a line are really undefined terms in geometry. A point on that line has no dimension. It has no width, no length, no height. It has no size. And the line has no width or height. It only has length. So it's kind of abstract. If a point has no size, then when I put a point on here, if I mark a point and let's say call it 1, that mark that I made has width. You can see it. But a point you really can't see. A point has no size at all. And so they don't take up any room on the line. And yet all of the points together make up the line. And each point corresponds to a real number. Once I decide where to mark 1, if I draw a number line like this and I put 0 on and I put 1 on, then all other points are determined, right? Because once I put 1 here, then I know 2 has to be there, and 3 is here, and this might be 2.5, and -1, and -2. All of the points, all of the coordinates of points, the numbers, now correspond to a point on the line. Once I have put the unit length, once I've determined that. Okay, so let's say that we want to find the point corresponding to the real number 1.345. Well, the first thing we might notice is that it is certainly between 1, so I'm going to mark this 1 and this 2. It's between 1 and 2, and this is divided into 10 little segments of equal length. So this is 1.1 here, and this is 1.2, and 1 3/10, and 1 4/10, and 1.5, etc. And we know that 1.34 will be somewhere in here, somewhere in this between 1.3 and 1.4. So let's zoom out. Let's see, let me get a different color here. Well, it's not working. So let me zoom out, and we'll call this 1.3. We're just zooming in here. And we're taking a closer look, and let's call this 1.4. And we have divided that into 10 little equal length sub-segments. And so we have 1.31, 1.32, 1.33, etc., 1.34, and 1.35. 1.35. Well, I can see that my number 1.345 lies between these two. Lies between these two numbers, 1.34, 1.35. So I zoom out again. And now this point down here I'll call 1.34, and this one 1.35, and divide that into 10 equal little pieces, and then this becomes 1.34 is here, and this is 1.341, and so on, 1.342, 1.345, 43, 1.344, and here we are, right here. So I could put the dot right here, and this is 1.345. But now back on our original line up there at the top, I don't know exactly how to put it in up here. It's between 1.3 and 1.4, and let's see, it's a little less than, I don't know, maybe I'd put it about right here. But again, we can't say. Here, I put that play. Whoa, jeez. I can't switch colors, sorry. So the point would be approximately here, and we would have seen that to begin with. But if you can keep zooming out and zooming in and zooming in and zooming in, you can make it more exact. So since points have no size at all, there's infinitely many points between two given points. And so we see there are, between any two real numbers, between any two decimal numbers, there are infinitely many more of them. So here's a question we might see in the future. Write an infinite sequence of numbers, all of which are between 0 and 1. So they're greater than 0 and less than 1. Well, there's many that we could do. Let's say this is 0 and this is 1 here. So first I'll show you how I could pick them. How about pick the one in the middle? That would be 1/2. And then I could pick half of that, which would be half of a half, or 1/2 squared, 1/4. And then I could take half of that, which would be 1/8. And half of that is 1/16, and so on. And we're just getting closer and closer to 0, aren't we? But we never get there. So here's the sequence that I got doing that: 1/2, 1/4, 1/8, 1/16, and in fact, in general, 1/2 to the n power. And it goes forever. Even 1/2 to the 50th is extremely close to 0. Too close for us to see. If we tried to plot the point, it would look like it was 0. But it isn't, and there's infinitely many more numbers smaller than that, but bigger than 0. Well, let's do another one. How about, let's call this 0 and 1 again. We're looking for an infinite sequence between 0 and 1. Why don't we do 1/2 first again? You could do many different examples. And then let's take 1/3. So 1/3. And then how about a 1/4? 1/4. 1/4. And then 1/5. 1/5. And you see what we're doing. We're getting closer and closer and closer to 0, but we never get there. 1/5, ... And in general, we could call this sequence 1/n. N equals 2, 3, 4, 5, 6, etc. So there's another infinite sequence of numbers that are between 0 and 1. And in fact, there's infinitely many sequences you could come up with. But those are just two. Real numbers are either rational or irrational. And first we're going to define what is a rational number. It has two definitions. One is that it is a real number, of course, a decimal number that can be expressed as the quotient of two integers. It can be expressed as a fraction. For example, we know that 0.5 is a decimal number and it's equal to 1/2. Or we could take 101 over 23. Any of these, minus 1 over 3. These are all written as fractions, and they also could be written as in decimal form. But any number that can be expressed as the quotient of two integers is rational. Another definition is it is a real number that has a terminating or repeating decimal expansion. Now by terminating, I mean something like 1.5. It repeats. If you wanted to call it a repeating decimal, you could. You could say it's 1.50000, and it repeats zeros forever. But we don't usually write it like that. We'll just call it 1.5. In Chapter 3, however, we will be thinking of 1.5 as having infinitely many digits. After the 5, though, they're all equal to 0. How about the number, 1.0123, 123, 123, ... Now the ... means that the 1, 2, 3 continues. Another way you can write that, if you wish, is 0.123, and you put a bar over the repeating part. This is a repeating decimal. And if it is then rational, we should be able to change it into a fraction, and we should be able to change fractions into their decimal form. Every fraction will either be a repeating decimal or it will just terminate. In other words, repeat zeros. Okay, so first we're going to see how to change fractions to decimals. You can always check your answer on the calculator, but remember your calculator will never give you an infinitely repeating decimal. It's going to round up or cut it off at some point. So, well, the easiest kind I didn't put down here, so let me, the easiest kind of fraction is one that has a power of 10 in the denominator. For example, 31 over 100. Well, when you divide by a power of 10, you're dividing here by 10 squared. You're going to move the decimal point to the left in the numerator. Move the decimal point 2 places to the left. So we have 31, and the decimal point, of course, is after the 1. You don't write that there. And move it 2 places to the left. So we have 0.31, or some people write 0.31. If you had 762 over 1 with 3 zeros, 10, no, let's put 4 zeros, 10,000. Well, you just take 762. The decimal point is to the right of the 2, and you're going to move it 4 places to the left. 1, 2, 3, and 4. So if you have a power of 10 in the denominator, it is very simple. You simply move the decimal point. Now for these other ones, well, let's do 6/5 next. Whoops. 6/5 I could write easily, since we have a 5 in the denominator, I could write 6 over 5 is equal to, and just multiply by 2 on the top and bottom, and I'd have 12 over 10. So if I have a 5 in the denominator, I can simply turn it into a fraction with a power of 10. That's 10 to the 1, so I'll move the decimal point in 12 1 place to the left, and I have 1.2. Another example, suppose we had 7 halves. You can divide the 2 into the 7, and you know you're going to get 3.5, but here's another way to do it. You can multiply by 5 over 5, getting 35 over 10, and then move the decimal point from the right of 5 once to the left, 3.5. So here what we've done is showed you that if you have a power of 10, If you have a power of 10 in the denominator, it's very simple. You move the decimal point to the left. If you have a 5 or a 2 as the denominator, then, or powers of 5, powers of 2, you can multiply by something to get it to be powers of 10 in the denominator, and do exactly the same thing. Now, you do not have to do it that way. You could use the next method that I'll do is for like 1/3. Well, here's the long way. You just take 3 and you're going to divide it using long division into 1. So the decimal point's here. 3 goes in 3. 3 times 3 is 9. And we have a remainder of 1. Bring down the 0. And you see that we're going to have 10 over and over and over again. So it'll be 3, 9, 1, remainder, bring down the 0. And you see that this is going to be 0.333 repeating. So 1/3 we could say is 0.3, and one way to write repeating, I can just put a bar over the repeating part, or you can just say 0.333 ... Now 12 over 7 is probably a little more complicated, so let's see. Let's start dividing 7 into 12. Now again, you can use your calculator, but you may not. It may round off and you won't really know what the repeating part is. So let's go through just one example so that you can see what happens here. 7 goes into 12 once, so I get 7 with a remainder of 6. Oh, no, 7. I'm doing 12 here. Okay, so 12. I get a remainder of 5, bring down my 0. 7 goes into 57 times. 7 times 7 is 49. I get a remainder of 1. Bring down this 0. 7 goes into 10 once. 7, I have a remainder of 3. Bring down the 0. We haven't started repeating yet. Let's see, 4 times 7 is 28. So 4 times 7, 28, remainder of 2. Bring down my 0. Oh boy, I think I'm going to run out of room. 7 goes into 20 twice. 2 times 7 is 14. And I have a remainder of 6. I still have not started repeating. So we keep going. Bring down 0. 7 times 8 is 56. It goes in 8 times. Subtract, we get a remainder of 4. Bring down the 0. Well, now how long is this going to last? I mean, when are we going to get a repeating part? To see this, let's circle the remainders that we have here. First we had a remainder of 5, then we got a remainder of 1, then we had a remainder of 3, and then a remainder of 2, a remainder of 6, a remainder of 4. As soon as we repeat a remainder, it's going to start to repeat. Well, think of this. If you're dividing by 7, how many remainders can you possibly get? If you divide by 7 and it doesn't go in evenly, you only have 6 remainders. You have 1, 2, 3, 4, 5, 6. That's all. So we're going to start to repeat soon. And watch how it happens. Okay, so 7 goes into 40. 7 times 5 is 35. So 35, remainder of 5. Ah, here we are. This remainder goes all the way back up here, and we have now repeated a remainder. So when I bring down my 0, it's going to go in 7, and I'm going to get 7, 1, 4, 2, 8, 5, etc. It's going to repeat. And I knew that if 7 was my denominator, that it would repeat after 1, 2, 3, 4, 5, or 6 divisions. So our answer is 12/7 is equal to 1.714285. Now, most of the time, you'll be able to tell this using your calculator, but I want you to be able to go through a couple of examples like this so that you really see what's happening. So we also should be able to change any rational number written in decimal form to a fraction, the quotient of two integers. Now, the first case we're going to do is when the decimal is terminating, or you could say repeating zeros. For example, 1.22. This is the real easy case. 1.22. Well, you'd like to get, integers don't have the decimal points at the end. We don't write it. So notice if I multiplied that by 100, I would get 122. So I'm going to multiply it by 100, but that would make it 100 times bigger. So I'm going to multiply it by 100 over 100, which is 1. Doesn't change a thing, and we get 122 over 100. And there it is represented as the quotient of two integers. Now, I'm not going to worry about reducing it to lowest terms. As you know, quotients of integers, fractions, have infinitely many ways to write them. And we can reduce it to its lowest term, which is unique, but we won't. Okay, the next one is exactly the same kind of problem. We have 1.0003. And I know that to move that decimal point to the right, I would want to multiply that number by a 1 with 4 zeros, 10,000. So I'm going to multiply it by, you could write 10 to the 4th, by the way. I'm going to multiply it by 1. Because then, if I multiply it by 1, I can say equals. Multiplying by 1 doesn't change anything. And when I multiply the 10,000 to the 1.0003, I get 10003 over, and the 10,000 is in the denominator. I mean, you can think of this as over 1, right? Multiply the tops, multiply the bottoms, you get this. And again, maybe we could reduce it. I don't think so. In fact, I'm sure not, because 2 and 5 are the only primes that go into 10,000, and they don't go into the top. So that one is in reduced form. Well, now we want to learn how to change numbers that are repeating, rational numbers that have repeating decimals, into fractions. We know that all rational numbers do have a representation as a fraction. Well, what do you think that 0.9999 repeating forever is? Look at this sequence of numbers up here. All of those numbers are less than 1, aren't they? Even if we had 0.9 followed by 100 more 9s, it's still a hair less than 1. So what do you think it is if the 9s repeat forever? Well, I'm going to prove to you that it is actually equal to 1. And here's how we'll do it. Now, keep in mind, 2 or 3 slides later, I have a method of doing this all written down for you. But instead of writing the method first, I just want to do these and let you see how it works. First thing I want to do is give the number a name. N equals 0.999 repeating. And then I want to circle the repeating part of the number. In this case, it's just 9. And I'm going to multiply n by the number that, the power of 10, that would move the decimal point to the right of that repeating block of digits. So that would be times 10. So 10n is equal to 9.999 repeating. And now I'm going to subtract n from it. In other words, I'm going to subtract 0.999 repeating, and I get 9 of them. 9n is equal to, and now look what happens here. All of the decimal part of the number drops out, and I get 9n is equal to 9, and this tells us for sure that n is 9 over 9, or 1. So this number is equal to 1. And these are the only kinds of numbers that have different ways of representing it as a decimal number. Let me kind of write that in the margins here. All real numbers that eventually repeat nines have two decimal forms, two ways of writing them. For example, 3.219999 repeating is the same thing as 3.22. They're equal. We can express decimals repeating nines in a terminating decimal. And those are the only kinds of rational numbers that have two ways of writing them as a decimal. We know that as a fraction, you can write something, like 1/2. We could write it as -2 over -4. We could write it as 100 over 200. There's infinitely many ways to write this number as a fraction. And that particular number, there is only one way to write it. Well, no, there isn't. It's a terminating decimal, so 0.5 is the way we would choose. But we could also say 0.4999 repeating forever. Terminating decimals can be written with repeating nines, but we don't ever do it. I just want you to see that the decimal representation of a number that repeats nines is not unique. And we'll do another example, changing repeating decimals to fractions. Here's our number. Let's give it a name. First, do that. It's worth it. 3.2222 forever. And circle the first repeating block of digits. Here it occurs right after the decimal point, and the block is just one digit. And I usually draw a little arrow like this. I know I'm going to multiply that by 10 to the 1, or 10, to move the decimal point past the first repeating block of digits. Now I'm not going to write up here on that number. I'm going to write 10n, a new sentence. 10n is 32.222 repeating. Now if I just subtract n the way I did in the last example, notice I subtract 3. Notice you have to line up the decimal points. Subtracting. And I have then again 10n minus one of them is 9n. And all of the decimal part goes away, and when we subtract we get 29. N is equal to 29 over 9. So this number here, 3.222 repeating, is 29 over 9. Here's another example, a little bit different. Let's give it a name. Take the time to do this. 0.012112, etc. Okay, so let's circle the first repeating block of digits right here. And so this time we're going to, in step 1, we'll multiply by a power of 10 to move the decimal past the first repeating block. So we'll have to multiply it by 10 cubed. In the second step, we're not going to subtract just n, we're going to subtract 10n. We're going to multiply this by 10. I want to move the decimal point to the right end of the block and to the left end. In the other two cases, the decimal point was already at the left end of the first repeating block. So let's see, we have 1000 n, multiplying it by 1000. What we get is, well, it's 12.1212, etc. And we want to multiply it by 10. So being very careful now, look, I have to line things up so that when I subtract, I don't make a mistake. Multiplying it by 10 is just 0.1212. Point, or you could put 0 point, repeating. Now you can see why I wanted to multiply by 10 in step 2. I didn't just subtract n. If I had done that, these repeating digits here would not have lined up. And so when I subtract, I get, well, how many n's? I have 990. N is equal to, and I subtract over here, all of the decimal part goes away, and I simply have 12. So n is equal to 12 over 990. And yeah, you could reduce it, but you don't need to. I just want you to know how to take a repeating decimal, change it to a fraction. How to take a terminating decimal, change it to a fraction. And how to change a fraction to a decimal. Now on this slide, I just have the exact method written out. If you need to write it down, just put it on pause and write this down. But in each of the 3 examples prior to this slide, we gave the decimal number that we were given a name, and I called it n. Gave it a name. And I circled the first repeating block of digits. I multiplied that number by a power of 10 that will move the decimal point past the first repeating block. In step 3, I'm going to subtract a number that I made by multiplying by the power of 10 that moves the decimal point to the front of the first repeating block. In example 1 and example 2, I didn't have to do that. I just subtracted n. But sometimes you have to multiply that by something in order to get the decimal parts of the 2 numbers exactly the same, to the right of the decimal point. Subtract and solve for n. So you could write down these steps and back up and go through the last 3 examples and see exactly how I used those 4 steps. In examples 1 and 2, I didn't need to use step 3. Okay, so now let's consider irrational numbers. The real numbers are made up of rational and irrational only. So if the rational numbers were numbers that could be written as a fraction or alternatively defined as a repeating or terminating decimal, then irrational numbers are simply not rational. So they would be, an irrational number is a number that cannot be expressed as the quotient of 2 integers. Cannot be expressed as a fraction. Or we could say, alternate definition, irrational number is a number that is a non-repeating decimal. So let's just look at some examples. Well, you know a couple of examples, pi, and let's see, I looked this up, I don't know all these. 3.141592654 ... You can see there's no repeating there. Pi is irrational. It cannot be expressed as a fraction. And of course we have our new number phi, which we know is 1 plus the square root of 5 over 2, the golden number, golden ratio, which is 1.618033989 ... Never repeats. And there's many ways that I could form an irrational number just making one up out of my head. For example, how about 4.01010010001 ... Can you see that it repeats a pattern, but it's a pattern that makes the decimal non-repeating. There's no single block of digits that keeps repeating. So these are irrational numbers. So this kind of reviews what sets of numbers we've talked about in MAT 103. The real numbers is the big set. That's all decimal numbers. And it has 2 kinds. It has the rationals, and rationals are the numbers that any of us actually ever deal with. We don't deal with exact representations of irrational numbers because we have to round off at some point to use the numbers. We have to change them to being rational. So, but we have rationals, irrationals, and then the rational numbers are the numbers we've been working in so far. The natural numbers we called capital N, and they were just the counting numbers, 1, 2, 3, etc. And we saw several sequences in those. We looked at the prime numbers, the Fibonacci, the Lucas. We've looked at the evens and the odds. The natural numbers, the integers, is the set containing, and I'm going to put 3 dots to the left, -3, -2, -1, 0, 1, 2, 3. So that's the next set that you learn about in school. First you learned about the natural numbers, and then you learned about 0 and the negative numbers. Those are called the integers. You need to know the names of these sets. And today we have talked about the rationals and the irrationals, and together they form the real numbers. So I'm going to end this video with 2 problems, and you'll see problems like this on our in-class set that we work on, and also probably on the next test. Find a rational and an irrational number between these 2 numbers here, these 2 terminating decimals. Okay, the way I do this is I write the biggest one on top, so I compare the digits and I see they differ right here. So the biggest one is 1.0026418, and it just continues with zeros, doesn't it? You might put in a few if you want. And now I'm going to leave a little space, and underneath it I'll put the smaller of the 2 numbers, 1.00264. Notice I'm lining up the oops, sorry, that should be a 7. 0, 0, 0. So I write the 2 numbers down, the smaller one underneath, and now I'm going to insert a number between. Trying to get. Okay, so let's insert one in between. We know that it will have the same digits out to where the digits are different. And now I want it to be bigger than the number underneath and smaller than the one on top. So I'm going to have the digit 7 here. If I put 8, anything I put after it would make it bigger than the one on top. And now I could put any digit I want here. Oh, let's just put 5. And we have a rational number. It's terminating. So my rational number, I'll put rat, might be 1.0026417.5. Now you could have, instead of 5, you could have 003 if you want, or you could have 6, whatever. But this part of the number would have to be the same in your answer. Now for an irrational number, as soon as I have the rational, it's easy. I'll just put the same thing, and now I'll put a tail on it, an infinite non-repeating tail. How about 0, 1, 0, 0, 1, 0, 0, 0, 1, ... So once you have the rational, you can just put a tail on it and get an irrational number between the 2. And then this is just a little problem to see that you clearly understand the definition of irrational and rational. Write a rational number having only digits 1 and 5. Well, that's easy. I could write 1.5, or I could write 0.1515, or 5.1515, or I could write 151.111111. These are terminating decimals. Or I could say repeating decimals. How about let's repeat ones forever? Those are rational numbers using only digits 1 and 5. I wonder, I'm not absolutely... I don't think we need to count the zeros after here as digits. This is definitely just using 1 and 5. Okay, but now for an irrational, using digits only 1 and 5, I could have 1 point. How about 5, 1, 5, 1, 1, 5, 1, 1, 1, etc. It's irrational because it's non-repeating, and it only has digits 1 and 5.